What is going on? I lost the strings, bro. Today we're going to do problem 764, largest plus sign. Okay, so let's go ahead and get right into this problem because I'm not feeling super well today, but that's no excuse, right? I can't use that as an excuse to deter me from taking advantage of the opportunity to solve a Leetcode problem and post the solution online. All right, so with that, let's get right into this problem. So you're given an integer n. You have an n by n binary grid with all values initially 1 except for some indices given in the array minds. The ith elements of the array minds is defined by minds I equals xi yi, where grid xi yi equals 0. Okay, so you can assume you have this grid where everything's a 1, and then you're given minds, and then you just set those corresponding grid cells to 0. Okay. Return the largest axis-aligned plus sign of 1s contained in grid. If there is none, return 0. An axis-aligned plus sign of 1s of order k has some center grid value equal 1 along with 4 arms, all of length k equals 1 going up, down. Oh, that's an L. Wait, what? Oh. With length k minus 1 going up, down, left, and right, made of 1s. Note that there could be 0s or 1s beyond the arms of the plus sign. Only the relevant area is... Okay, yeah, so you're not actually given this grid, right? You're given a size of a grid, so it's a 5 by 5. And then you're given the position of a minds, right? So 0, 1, 2, 3, 4, 0, 1, 2. That's the position of a 0, right? So basically to create this grid, you would just take this n by n dimension, create a grid of all 1s, and then look at each mind and then just stack in, right, where all the minds are. Okay. Cool. Okay. So then sorry, I haven't solved this problem yet, so I don't really know like how I'm going to do it exactly yet. What I'm kind of thinking of here first, right? So in this problem, there's actually there's actually a bunch of optimal solutions. So it's saying the optimal solution is this, right? This 2 by 2 here. Well, it's 3 by 3, but it's 2 from the center, 2 from the center, 2 from the center. So 3 by 3 squared, whatever, right? And that's actually not the only solution, right? So if I was to create this little square thing, you'll notice, right, there's one here, there's one here, there's one here, here, right? But there's no size 3 because of this 0, right? Since this 0's in this position, right, you can't have a solution where the arms are different lengths, right? So you can't have like an arm going out this way, like, oh, okay, well, this arm and this arm, so it's size 3, right? You can only they have to all be the same length on each side, right? So each side, each leg, we'll call them legs, right? So you have 4 legs, right? Each leg has to be the same length. So you can't have it such that like, you know, oh, this is a 3 because there's 3 and this is 2 or whatever, right? So I guess one key observation for this problem, right, is you're constrained by your shortest leg. Like, right? Because like in this problem, we were considering maybe a potential, let's say we were considering a potential cross, right, here in this position. Okay, well, in the up direction, where you say, wow, I have 3 up here. And then I ask in the left direction, and I say, okay, I also have 3 here. So it's like, this is looking pretty good. Like, there's a potential cross here. Imagine I don't know the dimensions of the array, right? So you're just kind of like, I zeroed in on just this position. Yeah, okay, I have 3 here, I have 3 here. This is looking pretty good. And then you look down, and you say, well, how many do I have below me? And it turns out you only have 1. But since you only have 1 going down, that means that you can no longer use all 3 going left, right? You can no longer use 1 going up. And you can no longer use... so then when you check going right, you check going right, you have just 1 as well. So that means that you can only create, using this center square, a length 1 system, right? So there's only a length 1 system here because 2 of your arms are only length 1. So even though you get a length 3 here and a length 3 here, you know, you're constrained by the lowest length cross that you can create, right? So I guess the best example of that, just to do it one more time here, is if you're given a system here, maybe you wanted to check this square. And you look up and you say, well, look at that, I have 2 up. And oh, look at that, I have 2 to the left. And oh, look at that, I have 2 to the right. Like, everything's looking good. But then when you look down here, you only have 1. So that means you can't use 2 to the right. You can only use 1 to the right. You can't use 2 to the up. You can only use 1 to the up. You can't use 2 to the right. Sorry, I said left and right wrong. You know, I can't use 2 to the left. I can only use 1 to the left because the shortest leg is 1. So the length of the cross I can make at any cell is the minimum length of the legs that I would connect to. And there's no diagonal legs, right? Somewhere here it says axis aligned, so I can't, like, just so you note this, if you're wondering, you can't, like, make a square like this, like a cross like this, right? Because that would be a valid cross if it wasn't axis aligned. But since it's axis aligned, what I need to do is I look at any cell, I say, okay, how long can this leg extend into the left? How long can this leg extend up? How long can this leg extend to the right? How long can this leg extend downwards? And the minimum of that is the cross that I can create, right? So that is the idea here. So an inefficient algorithm to do this. First, let's assume that we create this grid, right? We could look at each cell, and then we could travel upwards, travel to the right, travel downwards, and travel left, right? So I look at this cell, and I go all the way to the right, and all the way up, and all the way left, and all the way down. And then I make a decision. So I traverse here, I traverse down, I traverse left, I traverse up to find information. Gather that information, collect it, see what the minimum leg is in any direction. Jesus Christ, dude. People... Sorry. Go left, go right, go up, go down. Then play the same game here, right? Go right, go down, go left, go up. Then go here and try it again. Right, and I'll do that for every node. So this is very inefficient, right? Because we're given this n squared grid, right? And then we're going to have to look at each cell, each n squared cells. And we're going to have to go n left, right? At most n left, n right, n down, n up, right? Because you're going in one direction, so there's only one dimension. Like, well, think about that for a second. Like, if it's 2 dimensions, n squared, you break it down 1 dimension, doesn't matter, right? But if I'm looking at this cell here, in order to figure out how long my left arm is, I have to go n to the left, right? If I'm looking at this cell, I have to go n to the left, and I have to go n up, right? So that means that, oh, Jesus Christ, John. Dude, I swear to God, sometimes people I have them on high alerts. What's going on? I'm just going to move. Okay, so I'm going to make a big brain move here. Apparently I can't actually make a big brain move. I can make a massively small brain move. Okay, so Whatever, let's just continue as is. So what does that mean? So I have to look at each n squared cells, and I have to do 4 n operations. So that means that this is an n cubed algorithm. Right, because I look at each n squared cells, and then for each n squared cells, I have to go n to the left, n up, n down, n to the right. So that's 4n cubed, 4n squared, 4n times n squared, 4n cubed, or n cubed. So there's a faster algorithm that is, well, since I already have to make this, that's fine. That would, I guess, essentially is, if we're looking at this system, right? What we can instead do is find all the information about going left, about going right, right? Because, like, one thing you'll notice is, like, when I figure out going right here, like, how long is the leg going here to the right, I'm, like, doing that again here when I check for how long I go to the right in this one. So, like, I'm recalculating information. So what if we used, like, a prefix sum notion, and I just kept track, right? I kept track of the length of the limbs, right? The length of the legs going right at any node. So if I instead looked at this system here, right, I said, okay, let's find the length of the right limbs at any position. Right, so the length of the right limbs here is 0, because there is nothing to the right of this node. The length of the longest right limb, right, the length of the leg to my right here is 0. The length of my leg here is 1. The length of my leg here is, well, there's both of these, so it's 2. The length of my leg here is 3. The length of my leg here is 4. Does that make sense? What I'm basically saying is the length of the leg to the right of this node is 4, right? Because that corresponds to this 4 here. And I can just do like a prefix sum to do that, right? Like if I'm a 1, if my neighbor's a 1 and my neighbor's neighbor, right? If I'm a 1, wait. All right. So another way of doing this, it's so funny how you can do something, but it's hard to explain it. Okay, if I'm a 1, if I'm looking at this node, Jesus Christ, and my neighbor is a 1, and my neighbor has a leg of length 2, well, that means that I have a leg of length 3, right? If my neighbor's neighbor has a leg of length, if my neighbor has a leg of length 2, and my neighbor's a 1, then I can just attach that neighbor to the leg length, and I'll have a neighbor of length 3, right? So that's just a convoluted way of saying that you can easily generate this right-to-array efficiently. All right, and then it's the same game here, so we'll just, since they're identical, so nothing new here. So when we get to this last one, this node has length 1. This node has a right of length 2, right? This node, although its neighbor has a leg of length 2 to the right, it doesn't, its neighbor is a 0, right? One's neighbor here is a 0, so it doesn't get to attach its leg to it because it kind of halts that process, right? Now I no longer have a neighbor, right? This neighbor is 0. And then this one has length 1. So that's the right. And then you would just play that game for right, left, up and down. So I'll just do left. And then you can just assume that I did it for the other ones too, because I don't feel like writing all this out, because I think it makes a lot of sense. So 0, right, because there's nothing to the left of 1. This one, there's 1 here, 2, 3, 4, 0, 1, 2, 3, 4. You know, they're identical, then they're going to have identical. And then to the left of this one, 0, 1. To the left of this one, 2. To the left of this, well, this has 2, but since this is a 0, this becomes 0, and then 1. And then you do the same thing for up, right? So you traverse down the system, down the system, down the system, right? Then you do the same thing for up. You go up the system, up the system, up the system. And then at the end, right, if you look at any node like this, right, if I want to figure out, okay, what's the longest limb you have? Well, I'd say it's going to be the minimum of my right leg. So I have a right leg of length 2. Notice that information is cached. I don't have to count here, right? I can just look at this information here. I have a left limb of length 2. All right, again, this information is cached, so I don't need to count this system. And then there's going to be, I don't want to populate the whole system, right? But in here, there's going to be for up, or apparently, dude, I haven't drinking any coffee yet today, so that somehow justifies me being stupid, right? So right is this length here. For up, there would be a, for up, there would be a value, right, within this array, there'd be a value 2 right here. Right, imagine this whole thing was populated. I'm just putting one value because I don't feel like walking through the whole thing. Right, so for up, there'd be a value of 2. Right, I don't need to count this. I could just refer to this array. But for down, right, for down, I'm doing way too much stuff at once. For down, the value would only be 1, right? So it'd be pre-populated with the value of 1, of course, because, you know, this is only 1 down here. So then that would mean that, well, okay, I have right 2, left 2, up 2, down 1. The minimum is 1. So the entire cross that I can make here is length 1. Now notice I don't need to, since I pre-populated R, I pre-populated L, I pre-populated U, I pre-populated D, I don't need to traverse the system again to find the length of these limbs, right? The length of these legs. Instead, I can just use these catched R, catched L, catched U, catched D, and pull that information out. Now you might be arguing like, well, that seems pretty inefficient too. Well, to calculate R, it's going to take n squared time. To calculate L, it's going to take n squared time. To calculate U, n squared time. D, n squared time. So that's 4n squared time, right? So we got 4n squared. And then to calculate, we have to look at each n squared cell. But now it's a constant operation, right? Because it's a constant operation to check R, constant operation to check L, constant operation to check U, constant operation to check D. So then it's just n squared, right? So it's n squared cells, due to constant operation, it's n squared time. So doing this adds additional space, sort of. But since these are all n squared size, it's still going to be the same memory, right? Asymptotically, right? Because this is, we had to create n squared for this grid. So then we create an additional 4n squared cells. So that doesn't really affect our space, right? And then we just have to look at each n squared cell and do a constant operation versus looking at each n squared cell and doing an n operation, which would make it n cubed. So we've just removed a factor of n by using this prefix sum notion. So let's go ahead and do that. So we'll have our grid. I'll just call it matrix M. And it's going to have everything is 1 times n. For blank in range n. Sorry, I'm just trying to think about how I do this. And then we'll create up, down, left, and right. This is ugly. There's probably a better way of doing this, but whatever. Okay, so that's up, down, left, and right. So I'm just creating those up, down, left, and right catch arrays. And then let's place all of the mines. I'm an idiot. So these are all supposed to be 0. I was supposed to copy and paste, and I didn't. And I'm a very foolish man sometimes. Okay. Set all these to 0. And then let's add all the mines first. So for x position, y position, and mines, that means that m at x, y, right, equals 0. So we're just putting the mines into the system. Now let's process up, let's process down, let's process left, let's process right. So let's look, so let's do left first. So for I in range, so we have to look at each row. So for each row in range n, right, because there's n rows. So we look at each row, and then we look at each column in range 1 to length of n, to n. So I'm trying to think about how the code will work here. So this is a 1 because the neighbor is a 1, plus the value of the neighbor in the grid. So left of row cell equals left, same row, cell minus 1. So I look at the previous column, and I say, so the previous column has to be a 1 in order for me to make this a 1. So my previous neighbor is a 1. And that means that if my left neighbor is a 1, then I have a lim of at least length 1 plus however many plus the let me restate that. If my neighbor is a 1, then I have a neighbor to my left, right? If my left neighbor is a 1, then I have at least a length 1 neighbor to my left. So I have a left leg of length 1. Now, if my neighbor has its own length x whatever, has its own leg, then I would add in the length of its leg, right? Because if he's a 1 and he has a leg length to its left, then I can also use that as part of my leg length to my left. Sorry, man. Sorry. So not if all are C minus 1, if the matrix at this value equals 1, right? So if the matrix is a 1 here, then I can use it as a part of my leg to my left, and then I can add in whatever leg it has to its left. So we do that for... All right, and then we do the same thing for... Look at each column in range. Well, now we want to go from the other direction, right? Because we want to start here, and we want to say the same. We want to make the same assertion, but now we want to look to the right, right? So we say if m of r c plus 1. So if my right neighbor equals 1, well then I have a leg to my right, which is at least of length 1, plus whatever leg it has to its right. Okay, and then now we're going to do, for column in range n, because we're going to do up and down. For row in range 1 to n. Right, so if the row above me equals 1, then I have at least a leg above me of length 1 plus whatever length the row above me cell has, blah, blah, blah. It's so hard to think so hardly. Alright, for row in range n minus 2, -1. So again, yeah, this just means we're going in reverse, right? Python's weird range thing, annoying. Okay, if m of, so if the row of below me equals 1, then below me equals 1 plus below me r plus 1. Now you could probably condense this significantly, but I'm not feeling it today. So whatever. So this is going to take n squared time, n squared time, n squared time, n squared time. Even just creating these arrays takes n squared time. All right, and then we'll look at each grid cell, right? So we'll return the max of the min so the grid cell itself doesn't count, right? Only the length of its legs, right? Like this has, okay, no, so this is 1, so it is 1 plus, right? Because the length of my limb here is 1, 1, 1, and 1. One, 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 and 1. So you return 2. Okay, so it's the max of 1 plus the min of so I'm trying to think about how we're going to do this. So the min of what's above me at IJ, what's to the left of me, what's to the right of me, what's to the above of me, and what's below, left, right, up, down, and what's below me. Times if this cell itself equals a 1, right? Because if it's a 0, you can't consider it, right? Because the center cell also has to be a 1. Okay. For I in range, and for J in range, n. So basically what we're doing is we're looking at each grid cell, right? So we're looking at all IJ pairs. And then we're saying, well, if Mij equals 1, and so you could also just do this, but that's going to be a weird, well, whatever. We'll just leave it like this. So if this equals 1, because if this is 0, then this will 0 out. But if it's a 1, then it's a candidate. So then we have 1 in the center plus the minimum length of any limb above me, below me, to my left, and to my right. Now this is probably going to error because there's a lot of schnizznick going on here. But I have been programming for quite a long time. All right. Don't get weird at the end. Don't fail. Pass. Ooh, my arm hurts. Doesn't look so good, man. Seems very slow. No, that's fine. So what's the runtime? What's the space? Well, we've kind of already exhausted this conversation, but let's just go ahead and do it. So let's start with time. Right? So we've already been given n, so we'll just put it in terms of n, which is given. So this is going to take n squared time to create this array, 4n squared time to create these arrays. For each mine, we have to do something, but mines can never be more than n squared, right? Because mines only associate with like the mines in the system. So you can never have more mines than possible places for mines to go. So this is never greater than n squared, so we don't need to include it in our runtime. Okay, so n squared to do this, n squared to do this, mines time to do this, n squared to do this. All these things take n squared, so it's an additional 4n squared. And then n squared operations to find the maximum. So that's how many n squared? Like 8, 9, 10 n squared. But 10 n squared, big O notation, just n squared, right? So this is a big O of n squared. I prefer to do like that because it's like Python, right? And then for space, well, creating this is n squared. We have 4n squared to create this. So that's 5n squared. But again, that's just scaling with n squared. So this takes us... The brute force solution is n cubed time n squared space. The optimal solution is n squared time n squared space. The time is obviously... Now, there's definitely tweaks you could make to make this faster, but it's worst case runtime complexity is still the same, right? Because like maybe you could reuse information here, right? You could use the same array over and over again and then calculate everything to the left, find out what that value is, save it. Calculate everything to the right, see if it's less, save it. Calculate everything down, you know. So there's definitely ways you can make this, you know, tweak it to make it more efficient, but it's not going to affect, you know, what we care about most, which is this worst case time complexity, space complexity. All right, guys. That's all I got for you today. Peace.